Good morning, this is Dr. Turner for Integrated Math 2. Today we're covering 9.3, which is looking at surface area of solids. Most of the assignments in Unit 9 are meant to be review, and hopefully they are. If not, not a big deal. But we're going to go ahead and get started here looking at some of our two-dimensional shapes. As I've mentioned before with some of these assignments, it is possible to of course, use your notes always. You can use your notes, and you have a cheat sheet under supplemental resources for all the formulas for two-dimensional shapes. That includes both surface area and volume. A lot of students are more comfortable with volume than surface area, which is fine. But this assignment is going to be all in surface area. So there are, as I said, there are going to be formulas that you can use for surface area. However, just like with area and perimeter, where perimeter you have perimeter formulas, but I always have told you guys to just understand perimeter as being the distance around the outside rather than trying to memorize those perimeter formulas. Similarly, with three-dimensional shapes, yes, you need to know the volume formulas. Surface area, if you're comfortable with area formulas, then you can kind of get there without having to have the surface area formula memorized. But it's just really a matter of personal preference. Let's start out with a basic example. Let's say we have a rectangular prism. And of course, with the rectangular prisms, this could apply to cubes as well, same concept. The only difference between a rectangular prism and a cube is that in a rectangular prism, you have opposite sides that are congruent, whereas in a cube, all 6 sides are congruent. Okay, but in a rectangular prism, you have 6 total sides. You have a front and back, you have a top and bottom, and then you have 2 sides. So each of those are going to be congruent. Now, if you look at the cheat sheet, or you look at the back of your book, the surface area for a rectangular prism is going to be written something like this: 2 times, in parentheses, length times width, plus length times height, plus width times height. And it might be ordered a little differently, the variables might be a little bit different, but it's going to look something like that. So on the rectangular prism, this is representing the 3 dimensions: length, width, and height. Because a rectangular prism is made up of 3 pairs of rectangles, that's why we have 3 pairs of multiplicatives here inside the parentheses. So if I were to look at, let's say, the front and back according to this diagram, then I would have 2 rectangles that are the same, that have a length and a height. And then if I were to look at the sides, I have 2 rectangles represented by width and height. And then if I were to look at top and bottom, according to this diagram, I would have 2 rectangles represented by length and width. So if I were to do a problem involving rectangular prisms, me personally, I would be likely to just find the area of the rectangles and add them up. However, if you have the formula anyways, that could be a faster way to do it. So let's say I give you a rectangular prism, and I could draw the diagram out, or I could just list the dimensions in a sentence. But let's say I give you a rectangular prism with a length of 10 centimeters, a width of 3 centimeters, and a height of 4 centimeters, for instance. So, to use the formula for a rectangular prism, this would be 2 times length times width, so 10 times 3, plus length times height, which would be 10 times 4, plus width times height, which would be 4 times 3. And with your commutative property, you can interchange some of those a little bit, but this would end up being 2 times 10 times 3, plus 10 times 4, plus 4 times 3. Adding those together gives you a total of 82. And then 2 times 82 would give you 164. Okay. So let's say you didn't have access to that formula, and you wanted to use just kind of breaking it down into the shapes that make up the outside, that make up the surface area. Well, if you did that, then you'd be doing the rectangles here. So I would sketch out my rectangles. So I have 2 that are on the front and back. Those are 10 by 4s. Okay. 10 times 4 is 40, times 2 is 80. And then I have the 2 sides. In this case, these are 3 by 4s. 3 times 4 is 12, times 2 gives me 24. And then last, I have the top and bottom. Top and bottom are 10 by 3s. 10 times 3 is 30. Times 2 is 60. And if I were to add those three together, I also get 164. So either way, you're going to get the correct answer. It really just depends on, do you have access to that formula sheet and do you understand what it's asking you for? Or are you going to break up the shape into the particulars? Either way, you get the right answer. However, you need to put the correct units. On a multiple choice test, it's likely that you'll have 164 given multiple times. One might say centimeters, one might say centimeters squared, one might say centimeters cubed. Now, because we're dealing with three-dimensional shapes, students are more than likely to make the mistake of putting cubed as the unit because it's three-dimensional. But surface area is a two-dimensional concept. Imagine you had a box and you were wrapping it with wrapping paper, right? 2 dimensions represents how much paper you need. That's not taking up a certain amount of three-dimensional space. It's just wrapping it around the outside. So both these cases, your answer would be 164, whatever the units are, in this case centimeters squared, or square centimeters. So be mindful of that. So rectangular prisms aren't too bad. However, when we get into shapes that are a little more complicated, let's say we have a cylinder, for instance, well, that throws students off. Now, we talked about what the net of these looks like back in 10.1, but still throws students off a little bit. That's okay. So in a cylinder, you have a total of 3 shapes. You have circles that represent the top and the bottom of the cylinder. And then, remembering back to 9.1 with the wrapper idea, the outside of the cylinder, if you unfurled it, would be a rectangle. So, to find the surface area of a cylinder, we would need to add the area of these individual shapes. Area of a circle, of course, is pi times radius squared. So we would need to know the radius of the cylinder. And then the rectangle, that gets a little bit tricky. Now, of course, the height is going to represent the height of the rectangle here. But the length, the distance of the wrapper, is a little bit trickier. Now, if you, again, imagine a two-dimensional concept in three-dimensional concept in two-dimensional space, the length of that rectangle, the length of the wrapper, would be how far outside the cylinder or how far outside the circle it goes. Well, that's circumference. So here, this would be 2 pi r, which represents circumference. So those are the dimensions of the rectangle. Again, if you're using the formula sheet anyways, then you're going to see something like, in the book, surface area is given as either 2 pi r squared plus 2 pi rh, or they might factor out that 2 or even the 2 pi and leave it as r squared plus rh, or they could factor out the r as well. Depends on the book. Sometimes they factor it a little differently. But that's your surface area formula. Now again, if you don't have access to that surface area formula, then I think most students would be okay with coming up with, okay, what shapes make up this three-dimensional object? And hopefully they have the area formula memorized rather than the surface area of the three-dimensional shape. But either way, you should get the correct answer. So let's take an example. Let's take a cylinder here, and let's say I have dimensions. I'm going to give a radius of 14 feet, and I'm going to have a height of 24 feet. Okay. So you're going to either use the surface area formula or break down the shapes. As always for me, my preference is that you leave it in terms of pi. But pay attention to the instructions on the assignment. If it says pi, use pi. If it says use 3.14 as an approximation, then you're going to need to get your calculator out. But here, let's say first I use the formula. So this is 2 pi times the radius squared plus 2 pi times the radius times the height. So if you're asked to leave it in terms of pi, you're doing all the operations except the pi. So 14 squared, for instance, would be 196. Here, 14 times 24, that is 240 plus 96, 336. And then we're going to also do it times 2. And just so I'm not making a mistake here, let's pull up a calculator just to be sure. So I'm doing 2 times 196, that's 392. 2 times 336. So I get 1,124 pi. And that would be my final answer if I'm asked to leave it in terms of pi. Remember, this is surface area, so it's going to be the unit, feet, and then in this case, squared. You can get the same thing by doing the individual shapes, which is what I would do preferably, but whatever you're more comfortable with, that's fine. Okay. So we talked about rectangular prisms, which would also apply to cubes. We talked about cylinders. Okay. Then we have cones. Now, cones are a little bit trickier, specifically because the outside is not as simple as unfurling a rectangle. So the formula area for a cone is a little bit trickier because of that. It's still not impossible, but this one might be one where you want to look at an example or at the formula rather, just so you can kind of understand what it's supposed to be. Now, the curved area of a cone is given by something that's known as a slant height. So if I draw a cone here, you have a couple of things here. You have your height, you have your radius, and then here we have something that's known as the slant height. Most of the time this is going to be a right triangle, and so in an easier example you will be given the slant height. Surface area for a cone is given by the area of the base, which is the circle, pi r squared, plus the area of the outside, the curved surface of the cone, which is given as pi times the radius times that slant height. Different books will use it in different ways. Now, you could make this harder by not giving the slant height, in which case you have to use Pythagorean theorem to calculate that because this is a right triangle. On your formula sheet, you're likely to see this. You're also likely to see pi r squared plus pi times the square root of h squared plus r squared. And all that is doing is basically calculating L by using Pythagorean theorem. For my assignment, I'm not going to give that to you, but just be aware that if you were given a problem without the slant height, you still should be able to solve for it. So we'll go ahead and do this out now. Let's say I give you a cone, and let's say the radius is 4 inches and the slant height is 5 inches. Okay, which would mean the height here is 3. That's okay. So going through, you're going to do your formula, which is there we go. Which is pi times the radius squared plus pi times the radius times the slant height. Again, for me, I want you to leave it in terms of pi. You have 4 squared, which is 16. 4 times 5, that's 20. So that would add up to 36 pi, and then your units, because we're talking about surface area, that's going to be inches squared. Now this is these are only a few examples. It's going to cover the majority of the assignment. You also have pyramids that are thrown in there, and I could also throw in really any shape. But if it's one that you're not familiar with or one that's not on your formula sheet, that means you want to break it up into the two-dimensional shapes, find the areas, and add them together. But that's it for today, guys. If you have any questions, please reach out to me. Otherwise, have a good day, and I will talk to you soon. Bye.